Good morning to everybody, and welcome to this second lecture of this course on the latest application frontiers of on-chip interconnection networks. And today, the focus is going to be on the potential that networks on chip have to foster system innovation in fog computing. So let's wrap up on what we said last time. Last time we saw some case studies from the early days of networks on chip. In particular, we saw that in the early days and for roughly a decade, even more, people were trying to adapt the interconnection network concept to match the distinctive features of an on-chip environment, which is more tightly constrained in terms of the research and power budgets. However, we also saw that this appears to be a never-ending story because the system keeps evolving. We saw the use case of emerging system integration technologies such as 2.5D and 3D integration. And we saw that this kind of adaptation to an on-chip environment is still alive. And for instance, today we are investigating about topologies for the new integration scenarios. At the same time, we learned some important lessons on the onset of a new interconnect technology. So we saw that in the early days, there was an intensive cross-benchmarking effort between state-of-the-art buses and networks on chip. And the industrial uptake of networks on chip happened not because this was a perfect solution. It had some pros and cons, but because it was meeting a pressing need, and the need had to do with the system level design. It was bringing a benefit to the system level designer, for instance, reduced energy for executing specific workloads, although the interconnection network was actually consuming more power. And I think this is still a very instructive lesson when we approach a cross-benchmarking of emerging interconnect technologies. We shouldn't expect these technologies to be the absolute best from all the possible quality metrics, from the viewpoint of all the possible quality metrics, but still we need to bring some relevant benefits to the system level designers. And investing on technology maturity is not enough for that. You need design automation support for that. That's why there is a rising star in the research community, which is design automation for emerging technologies. Last but not least, since we are talking about an emerging technology, only large volumes can amortize the cost for the industrial uptake of these technologies. Okay, so after this adaptation effort to the constraints of an on-chip environment, what came next? What happened next was that network on chip designers started to co-design more and more the network on chip with the system architecture. And so the point is that, isolated partial solutions that have as the only focus the network on chip are going to soon run out of steam, okay? But what happened was that people were increasingly designing the network on chip for the system. And from this viewpoint, we had two directions. On the one hand, there was an actual co-design, and there is currently still an actual co-design of the network on chip with the system architecture. Let me make some examples, and one relevant example will be made today in this lecture. So think about testing. If you think about testing support for your network on chip, it hasn't to be an isolated solution. It has to be integrated into a system level testing strategy. For instance, you may want to use your network on chip to carry test pattern for the processing cores. So use it as a test access mechanism for those cores. Think about fault tolerance. If you try to implement fault tolerance in hardware only, it's going to be overly expensive. A better approach could be to co-design your fault tolerance support in hardware and in software. A relevant example of this is given by the well-known checkpointing and rollback technique, which needs both hardware and software support. Similarly, if you think about synchronization, so synchronization, any synchronization interface that you want to implement in the on-chip interconnection network has to do with a system-level power management strategy. Assume that you want to implement voltage and frequency domains, especially at a fine granularity. You have a design space to explore there. You may want to have your network on chip split into the voltage and frequency domains of the computation tiles, or you may have your network on chip as an independent voltage and frequency aisle. There are trade-offs, and you need to assess the trade-offs at the system level. Similarly, shared memory multiprocessors come with typically cache coherence protocols, and you may want to accelerate the typical communications that are involved in a cache coherence protocols in your on-chip interconnection network through special hardware support. For instance, you may want to provide hardware support for multicast, for broadcast, that are common operation in any cache coherence protocol. Another trend was actually to implement some form of assistance in the network on chip for some functions that are performed by the system software, by the operating system, or by the hypervisor level resource manager, or even to co-design your network on chip with the application layer. For instance, applications may require latency and throughput guarantees, and the only way to provide such guarantees is to implement quality of service support, such as bandwidth reservation, in your network. Moreover, you can have a virtualization of your computing platform. In this case, you need to support isolation between virtual machines, and in that case, having even a traffic isolation support in the network on chip is the perfect way to complement the isolation features of the operating system. Moreover, you may have, let's say, thermal power delay control. Delay control means that, for instance, your network on chip may have mechanisms to quantify local delay variability with respect to nominal delay. And you may use this to use in situ adaptations mechanisms to operating conditions, or you can report this to an operating system that will use this information for mapping applications. Also, today we have emerging workloads, for instance, associated with machine learning. You may want to specialize your network on chip to efficiently support this kind of communication workload. Last but not least, you may want to take care of platform security, especially in the network on chip, in addition to the system as a whole, because through networks on chip, for instance, you can conduct denial of service attacks, or you can leak out informations depending, for instance, on the delay that malicious packets are meeting in order to access shared resources on the platforms. So my goal was to give you the idea that today, don't work on networks on chip in isolation, but design your network on chip for the system. And from this viewpoint, network on chip design is not an isolated discipline anymore, but it starts to break the barriers between disciplines. So it's a highly interdisciplinary research task. Now the question, the most interesting question is what's next? Okay, what's happening today and what will happen in the future? So my viewpoint is that this trend to co-design the network on chip with the system architecture, the system software, the resource management, and even with applications is far from running out of steam. Instead, it's gaining more and more momentum. It's widening the scope. We have already seen that the only way to sustain the level of system integration is through emerging 2.5D and 3D integration technologies. And we have seen the effort that is ongoing to extend networks on chip for this domain. At the same time, networks on chip are not co-designed with the system architecture only, but the new frontier is to co-design it even with a system of systems. This may appear to you to be a little bit exaggerated. And in fact, this is a typically overlooked opportunity. But this is exactly the reason why today I will have the lecture that we'll have. It will be exactly on this. A more popular trend instead is to draw the ultimate NoC level implications of emerging computing paradigms. We know, for instance, that many applications can tolerate errors while still delivering reasonable accuracies. Think about pattern recognition, machine learning, image processing, and the like. So approximate computing has emerged as an attractive computing technique to trade accuracy for performance or power. And we can extend exactly the same concept to the communication domain. So we can approximate the communication data, monitoring the implications on the application accuracy. Other computing paradigms instead leverage the biological inspiration. And for instance, in the case of neuromorphic computing, they obtain energy efficiency by exploiting asynchronous event-driven computation. These neuromorphic computing systems, therefore, require an event-driven communication architecture as well, that is asynchronous interconnection networks, and this will be presented in the next lecture. At the same time, deep neural networks are increasingly executed on top of multi-core processor architectures. And in this context, the network on chip can be optimized to accelerate the execution of training or inference workloads, or deep neural network algorithms can be parallelized with communication awareness, which has been shown to bring benefits. Interestingly, people are not only specialized in the network on chip for deep neural network workloads, but they are increasingly using artificial intelligence to design better networks on chip. For instance, they are using artificial intelligence to, in particular, they are using deep reinforcement learning to explore the vast design space of an on-chip interconnection network, especially in 2.5D and 3D integration scenarios, or to change, another example, to change reactive fault tolerance strategies into proactive fault tolerance strategies. But more on this will follow in the next lecture. Overall, the trend is clear. Aligning network on chip design to its fast evolving usage context leads to vertically integrated end-to-end solutions, and this has high potential for technological breakthrough. Last but not least, don't forget that there is a background question that it's not losing relevance over time, it's not getting adequate answers, so to say. So I call this a persistent question, but it's going to stay for quite a long time. And the question is, shall we keep using electrons to convey information over the silicon chip, or shall we take advantage of emerging interconnect technologies such as silicon photonics, wireless networks on chip? So despite the amount of publications, the answer today is not clear nor convincing. However, the role of communication in current largely parallel system is such that this question is not going to lose relevance, in my opinion, for the next 5 to 10 years. Okay, after this introduction, which completes my review of the network on chip history from the early days to the current situation, that also allows you to understand what's going on today, it's time to go into some technical details. And today, after reviewing the last time network on chip for 2.5D integration, today I will explore the potential that the networks on chip have to foster system innovation in the Internet of Things environment, and especially for fog computing. Today, people, Internet of Things services, and richly connected intelligent devices or smart devices or smart things, depending on the terminology you want to use, are being increasingly weaved together in emerging information systems. Many of such emerging application domains make use of devices and products that are capable of sensing the environment or the human body, and use a vast amount of sensing data to perceive, model, and adapt to the environment and to the users. And this requires little or even no human intervention, no human interaction, delivering so-called smart services. Examples, as you can see here, range from smart homes to smart cities and transport networks, from smart e-health to smart industry and smart energy networks. There are a few emerging questions in this domain that are highly investigated by researchers in distributed systems, especially in that domain. So how do we provide these kind of services? On which devices are we going to process data to run the associated computational workload? Who is going to own and manage such devices? How do these devices interact with each other? How do we compose services together from different providers on the same device? So, in order to start answering some of these questions, because these are open and hot questions, we need to boil this picture down into some implementation details. We find out that at the core of most of these applications, there are two fundamental building blocks. On the one hand, on the lower side of this slide, we have smart objects or IoT device layer. These devices or objects are able to sense, actuate, store, and to some extent also interpret information created within themselves or sensed from the surrounding environment. And they are able to either act on their own or to collaborate with each other and exchange information with other kinds of electronic devices and human users. On the other hand, we have the cloud computing infrastructure. It is used for large-scale data processing and is powered by strategically located data centers with very large aggregate resource capacity, such as CPUs, GPUs, storage, and so on. As a matter of fact, the computational workload associated with many Internet of Things services is typically offloaded to the cloud, where you can easily apply big data methodologies and tools, and the results of these computations are returned back to the intended users. This is for sure the way early IoT services used to work. They were offloading most of their computation to the cloud. However, a new trend is gaining momentum, which consists, as you can read from the title, of bringing some form of intelligence at the so-called infrastructure edge, that is outside the cloud infrastructure. This trend is certainly pushed by the advances in IoT technologies, in embedded computing in general, which have made the powerful sensing and actuating devices available with increasing compute power and storage capacity. Similarly, a number of higher-end devices are currently appearing, such as Raspberry Pi, Android-enabled smartphones, NVIDIA Jackson TS2, Xilinx Versal platforms, just platforms that aim at some form of high-performance computing while taking into account the research, the tight resource budget that you have in an edge computing environment. Well, when we put together all the devices that can perform some kind of computation, distributed computation at the edge, from intelligent sensors, all the way to high-end nodes that you may want to instantiate in hospitals, cities, railway stations, and so on, then you get a hierarchy of compute power. This is a distributed data path. This is a distributed computation infrastructure. This is a hierarchy of compute power that typically collects, aggregates, and processes data from IoT devices and sensors and processes them directly at the infrastructure edge. In the middle of the picture, you can see an embodiment of the concept of intelligent edge for IoT analytics. Typically, the set of devices that lie halfway between IoT devices and the cloud are indicating as the fog computing layer. And in this picture, we can see an example of a fog computing layer from an important paper published in 2017 on IEEE intelligent systems. So why you would like to bring intelligence at the edge? Today, there are a number of good reasons why you would like to do that. Minimize latency, because there are many applications that require immediate insight and feedback, and you cannot afford offloading your computational workload to the cloud. It takes too long. Reduce bandwidth, because sending big data back and forth from things to the cloud can consume enormous bandwidth and also consumes large cost. No? the access paradigm of the cloud is pay-as-you-go or some other dynamic pricing scheme. Another advantage of staying at the infrastructure edge is that you end up reducing threats. In fact, when you transfer data across the campus, state, country, or even an ocean, it's simply more prone to attacks and breaches. And processing data at the edge can reduce security vulnerabilities. You avoid duplication because if you send all the data to the cloud for processing, for sure you're going to have some duplication in terms of memory, storage, networking equipment, software, and so on. You can improve reliability because even without any nefarious activity from hackers, data can be corrupted on its own. Okay, we all know that when you are involved in a cell phone call, typically this breaks up or drops. You want to maintain compliance because there are many countries that forbid companies from moving the personal data of their citizens outside their borders. Overall, all these considerations, in my opinion, justify the current unmistakable trend, which is to bring intelligence at the edge, thus going well beyond cloud-based centralized Internet of Things platforms. One thing that you should bear in mind is that there are currently lots of difficulties in changing this distributed data path, this rising compute hierarchy, into the onset of a full-fledged ecosystem of smart IoT services. So to say, the availability of hardware, the increasing availability of hardware is not easily translating into business on top of it. Why? The reason is because IoT devices, fog devices in the cloud are currently somewhat loosely coupled in the best case. And this is the reality of our system today. There are boundaries, there are hardware gaps, there are software gaps, there are boundaries between these systems. Why? Well, many potential market players today are still faced with the challenge of building and deploying the entire end-to-end software, hardware, and communication infrastructure for to deliver smart services. This is a barrier to entry, the cost of setting up the end-to-end service. In order to streamline application deployment, this would require some form of interoperability between the components of an end-to-end IoT smart application. But this is currently hindered by a myriad of different protocols, platforms, and software APIs. Major exceptions only occur when an end-to-end solution can be developed in-house and from scratch by a single large and strong organization. But this is not the definition of an ecosystem of IoT services delivered by a myriad of service providers. At the same time, a way to cut down the deployment and maintenance cost of computing platforms would be to share some platforms, to share their computing capability. Unfortunately, people typically use commercial off-the-shelf edge computing platforms, even high-end ones, but these platforms are typically designed to be single-tenant proprietary platforms. So with no support, with limited support for efficient and secure sharing. Even in case some support for some form of virtualization is provided, even in that case, resource managers typically only support rigid and moldable jobs, to use an HPC terminology. That is, they implement only static resource management. This static nature of resource assignment and management is at odds with the characteristics of the IoT environment, which is extremely context sensitive. It is extremely dynamic. So in most IoT applications have fluctuating workloads over time. They have processing peaks that are triggered by external events. And so it's at the opposite extreme of a static resource management policy. So, summing up, this gives you a clear idea that although we have a distributed data path, a new hierarchy of compute power, it's not a computing continuum yet. And this is actually what I'm trying to look at today. And that's an open issue for the research community as well. And this has high practical implications. Today, people are searching for a cloud, searching to implement a cloud things continuum. So a quasi-continuous segment that connects the cloud with IoT devices, and along which you may think of flexibly instantiating your Internet of Things services. Think about the fact that governments are putting a lot of money to make this happen because this has relevant business implications. The European Union has allocated roughly 50 million euros to make this happen in the last couple of years. However, the question that you now address is how to make this happen. What could be a foundation for the design and management of a compute power, of a compute continuum? Because a compute continuum means to put many things together, many different things together, and to orchestrate them. But you need a leading idea, a guiding principle to put all the things together. Well, one inspiration comes directly from the distinctive features of the IoT environment. The feature that I'm going to present is typically viewed as a challenge for hardware and software design, but indeed it can be seen as an opportunity, as we will see shortly hereafter. The fact is that there is a lot of dynamicity in an IoT environment, which means that there are a lot of different things that change, and that change in a poorly predictable way. So let's see some examples of this dynamicity. You may have dynamics of the applications. So if you look at what happens in a fog node, here you have applications that dynamically come and go. These applications, this workload may be offloaded from IoT devices. They can be offloaded from the cloud, or you can in turn migrate running workloads to the IoT devices or to the cloud. Applications, that's not a mystery, have different phases, and these phases typically are not exploited for optimization of the execution state, for instance. Applications have goals that evolve over time. Today we talk about dynamic goal management. It means that think about a tablet. It may have an application running associated with a given IoT service, and the goal may be to maximize throughput. But when it runs short of battery charge, then the goal may be changed into save as much power as possible. Moreover, the input rate of data streams sensed from the environment can be irregular, unpredictable, and vast in nature, depending on what happens in the surrounding environment. Last but not least, not all input data have the same utility for the user. For instance, your camera may keep getting pictures that are very similar until something different happens, and at that point, the new set of images have a lot of importance for the end user. We also have dynamics of the platform states. On a fog computing node, we have heterogeneous resources, because today the mainstream computing paradigm consists of heterogeneous parallel computing. And you have several applications that contend to use these resources. And these applications may have conflicting goals that have to be harmonized over time. And the optimal mapping depends on the execution context, how many applications are contending for these resources, and what's the phase of this application, because you can instruct these applications to ask just what they need at a given point in time. Also, the platform state is changing in terms of reliability, availability, and performance, due, for instance, to physical layer effects such as aging, wear out, faults, and so on. And also the thermal map of your system keeps changing at runtime, thus requiring some form of thermal control. Last but not least, you have environmental uncertainty. The number of users associated with the specific IoT services, making use of these services, changes over time. The quality of communication channels change over time. Users are mobile users. Therefore, they may associate their workload to different fog devices. Last but not least, the availability of sensors and devices, of IoT devices, is not constant over time. So the point is, can we change this problem, so to say, this design issue, so to say, into an opportunity? Well, to do that, you need to start having a new mindset to approach design problems in this kind of systems. Really, new mindset is needed for the system level designer, for the researchers. Let me give you some examples. You have to stop allocating resources for the worst case. This is never a good idea. This is especially a bad idea in this context, where the workload is fluctuating over time. A better idea could be instead to use what you need at any given point in time, to request to a resource manager what you need at a given point in time. You may also think of dynamically assembling resource pools. There are some advanced computer organizations that are called disaggregated architectures, where you have resource pools and where you build your own platform on the fly. And here, silicon photonics has a promising future because it enables to view these resource pools as though they were local to each other due to the high speed of silicon photonics. Moreover, you have to start correlating quality of execution to resource availability, so that you can define a target quality of execution and you can request resources for that. Moreover, we need to start considering the pricing scheme when requesting for resources to a resource manager, because resource providers may enforce smart billing strategies, so to encourage the use of resources during off-peak hours, so that they have a more uniform utilization profile, and this results into the abatement of maintenance costs. This is an ideal context to apply the latest developments on artificial intelligence, because you may take not only reactive but also proactive resource management decisions based on the learning of predictive models. Last but not least, this new mindset is fostering new concepts, and the new concepts have to do with the self-star properties. In particular, there is a rising star, which is the rising star of self-aware systems. Okay, a self-aware system is a system that has something special about a deep understanding of itself and of its environment in the context of the goals of the systems. And here there are some useful readings in order to help you to put together this new mindset to approach problems. These readings come from different domains. They span different abstraction layers. This is done on purpose, because the basic idea is to convince you that there is a lot going on in different fields at different abstraction layers to embody dynamicity of modern computing systems, and to draw the ultimate hardware software implications. Well, a way to change the uncertainty and dynamism of a computing environment into an opportunity is through the concept of elastic computing. The term elasticity comes from material science. It actually indicates the property of returning, the property of a material of returning to an initial form or state following deformation. Well, the elasticity paradigm, if you think about it, it's already mainstream in cloud computing, because cloud computing implements the elastic provisioning of virtual resources, but this happens at a coarse granularity. An important thing that you should keep in mind is that cloud elasticity is delivered at the level of the service architecture. What it means in practice, to simplify a little bit, is that service replicas are created to respond to increasing workloads. So the resource allocation granularity is pretty coarse-grained. You add or subtract resources to a user at a coarse granularity. But this kind of elasticity cannot be naturally implemented as is the infrastructure edge, because this is a much more constrained execution environment. Therefore, at the edge, resource elasticity should be implemented not at the service architecture level, but at the service model level, the service level. And the granularity of resource allocation should be individual processing elements. In practice, individual services should be in a position to be given more or less individual processing cores on your fog computing node, or to modulate the time slot, modulate the duration, the time slot for accessing shared resources that cannot be spatially separated. Okay, so you need some form of fine-grained modulation of the usage of resources at the infrastructure edge. So elasticity needs to be brought into completely new ground. This is more challenging, and the environment is highly sensitive to any form of reconfiguration overhead. So it's really a challenge. Well, how would an elastic hardware-software system work? Let's consider this re-elaborated acquisition and processing pipeline. You have here a 3D stacked in focal plane vision chip from Leti, or you can have any other form of smart sensor, and it has some local computation capability. Then you have, moving up the hierarchy, an heterogeneous parallel IoT gateway or fog node, and finally you have cloud resources. And this is a zoom into a many core accelerator into the IoT gateway. So what happens is that there are asynchronous events that are dispatched from the smart sensor to the gateway. For instance, as I was telling you before, you may have a camera that starts sensing something interesting. Okay, the non-interesting things are filtered out directly by the vision chip, but interesting things are dispatched to the next level of the compute hierarchy. And here you start having a pulsing compute partitions. So from time to time, you may have to ask more resources to process these asynchronous events that are coming, that are dispatched from the smart sensor. Similarly, you may have distributed deep neural network models. A simple way to do that is to have a small deep neural network model executing directly in the vision chip, and you may have some form of estimating whether the inference of this small deep neural network model is trustworthy or not. You can have special techniques to do that, such as monitoring. If the inference is not deemed trustworthy, then you can hand over your input data to the next level of the compute hierarchy and run inference through a larger deep neural network model, taking more resources. Again, you end up having parsing compute partitions on the gateway. Or data could be annotated based on their importance for the end user, based on their value of information, to use a formal term. And based on this value of information, we can allocate more or less resources on the gateway. Last but not least, you can have energy-aware computing. So you can compute things in the sensor node as long as you have battery. When you're running short of battery, the computation is offloaded to the gateway. So you see here that you start having elastic compute and memory partitions. Similarly, you may want to offload some computation kernels from the cloud to the gateway in order to exploit untapped computing resources on the gateway. And we know all the advantages this is going to bring you. At the same time, if the complexity of the computation on the fog node skyrockets, or whether you have too much contention, you may do the other way around. You can offload computation to the cloud. So to use a formal term, you can implement dynamic deployment of the service topology. So think about the mini-core accelerator of your fog node, of your gateway. Even in this case, you can use elastic computing for opportunistic optimization of the execution state. Think about these compute partitions. You may have the green partition that is a periodic task. So it periodically comes and goes. When this task goes, you may opportunistically use the freed resources in order to give these resources to the yellow partition, which is going to extend. And then it is going to shrink back before the next iteration of the green partition. And this makes sense, obviously, only if you have a fine-grained and fast dynamic reconfiguration mechanism for hardware and software in place. Moreover, if the blue partition completes execution, then you may want to relocate the violet partition, for instance, in order to minimize the average distance of cores to the memory controller. Moreover, in the context of some thermal control strategy, you may want to migrate the tasks of the violet partition from a hot region to a colder region. Last but not least, you may have a yellow partition that suddenly needs more resources because there is something interesting going on in the environment. Therefore, you enlarge it, you give it more resources. Maybe that's not enough. So you migrate the lower yellow partition to the left, and you make more room for this partition, which is becoming critical. So lots of opportunities for execution state optimization. What are the benefits of an elastic Internet of Things service, of elastic applications? Well, elastic applications need not be constrained by the current execution context. It's not that if you don't have the resources, there's no way to run. No, you can run anyway. You just have to remodulate your quality of execution. Moreover, you can stop allocating computation and storage resources for the worst case. And you can start asking only for what you need at a given point in time. Elastic applications can more effectively share resources. Moreover, it's possible to perform dynamic goal management because you can match the goal of your execution to the execution context and to the platform state. You may enable services to take smart mapping decisions, such as asking more resources on the fog node or to be directly migrated to the cloud. Moreover, adaptivity and elasticity are key for safety critical software that could adaptively respond to unexpected situations in a manner that prevents loss of life. For instance, you can give instantaneously all the resources that this kind of safety critical applications require upon detection of a critical situation. Last but not least, as I've shown in the previous slide, this opens up unprecedented opportunities for optimizing the execution state. Again, these are a number of useful readings about the concept of elastic computing and how it's slowly coming to the forefront, starting from different perspectives. Okay, so I have introduced the scenario, the context, and it's needed. You can ask this, you can say this has nothing to do with network on chip. That's false. That's to introduce you to the mindset that a network on chip designer should have nowadays. First of all, try to become aware of the usage context of the scenario and then design your network on chip for it. So now we're going to take 5 minutes break. Meanwhile, you can post your questions, and when I resume the presentation, I will try to answer the most relevant or let's say strategic questions. So talk to you again in roughly 5 minutes. Okay, it's time to move on. Let's look at this question. It's not a question, it's a consideration. That it's good to get to know the system you are designing your component for in order to have relevant, practically relevant research. The point that I'm trying to demonstrate is that it's not only this, which is anyway an important takeaway, but it's also that when you talk about these high-level visions, you talk about these systems of systems, you may think that the network on chip is something buried at the very bottom of the software hardware stack, and you can treat it just as yet another commodity component that you will use later on to build your system. Okay, so you define the way your system is going to work, and later on you have to do with the network on chip, but consider it just as a commodity component. But the point is that the network on chip was born and is a system integration framework. At least it is a first layer of the system integration framework. Therefore, there are important opportunities to co-optimize the network on chip with the system and even with the system of systems. So this has two implications. You may wonder what are the ultimate NoC level implications, NoC level optimizations that are requested by this vision. This is the first way to go. This is a top-down approach. I have a vision, and I wonder whether this has this opens up optimization opportunities for my NoC. But on the other hand, as a NoC designer, and I'm actually a NoC designer, you may have NoCs with special features, and you may wonder whether it's possible to build systems and even system of systems around this. For instance, my specific, not general, of course, idea about how to implement compute continuum is rooted exactly in my expertise on chip interconnection networks. So I historically started from some special isolation features implemented in my network on chip, and the next step was to find an application for it. And I surprisingly found out that this special support that I had in my NoC was actually meeting important system level requirements and even system of system requirements. It was actually meeting this requirement to build a compute continuum. And the whole continuum could be centered around the characteristics of my chip interconnection networks. So you can go top down or bottom up, but the important thing is that you search for an end-to-end cross-layer optimized solution. Okay, let's move on. Now, let's go deeper into some technical detail. In fact, I think it's clear that you can build a new compute continuum around the concept of elastic computing. And elastic computing is nothing else but dynamically remodulating the amount of resources assigned to different applications, to different IoT services that share a platform and that ultimately share the compute continuum. So now let's draw the implications of this for a fog computing node. As I told you, the way it came out was completely opposite. I started from the bottom, from the network on chip, and I built a system on top of it, then finding out that it was meeting system level requirements. But for the sake of teaching, for the sake of tutorial, I will follow a top-down refinement approach. So if you think about your fog computing node, that is a computing node with relevant processing and storage capacity, and that lies halfway between IoT devices, low-end IoT devices, and the cloud. Because of elastic computing, we have an efficient way to share it among multiple IoT services. And so from this, we can derive interesting design requirements for our fog computing node. So first of all, it will be shared. And let me remind you that today there is only poor support in commercial off-the-shelf platforms for efficient and secure sharing. So we need, first of all, a low overhead sharing mechanism for the fog node. For instance, for largely parallel processing architecture, the mainstream sharing mechanism consists of time division multiplexing, which is anyway pretty inefficient because either you have time division multiplexing at a coarse granularity, that is, you run all the tasks to completion and then you hand over the resources to another task for another set of time slots, or you implement it at fine granularity, but in this case, you need to sustain the cost for context switching. And this needs to be supported in hardware, and it's overly expensive. Moreover, security is an important requirement in an IoT environment. So you need to make sure that the aggregated services, the aggregated applications that are running on your fog node are actually isolated with respect to one another. And therefore, you need to implement an integrated hardware software support for security. So if you think about your network on chip, you may have a malicious entity that keeps flooding the network on chip with packets in such a way that all kinds of activities are blocked. Or it can interfere with the communication activity of a service in such a way that it fails to meet real-time requirements. Moreover, if you have been authorized to enter the system, but you are a malicious entity and you are contending for accessing shared resources, you can monitor the delay for accessing these shared resources in order to leak out information about what the system is actually doing. Last but not least, the key requirement for elastic computing, for especially resource elasticity, is to have an efficient dynamic reconfiguration mechanism in place. You should dynamically change the amount of resources that you give to running IoT services. And this requires hardware support because you have to do it fast. And while reconfiguring the resources, you don't have to miss the security property. So the question is, have these requirements anything to do with the on-chip interconnection network? Clearly, they are highly related to the network on chip, but first, before getting into this detail, let's take a look at the target architecture of the fog node. So a target fog node architecture may consist of a heterogeneous parallel computing architecture, which is kind of mainstream today. You can have a host processor that is suitable for coarse-grained parallelism and that performs system-level control tasks, and that runs a full-fledged operating system extended with a separation kernel, that is with a kernel that guarantees spatial and temporal isolation of running applications, and that keeps their interactions under tight control. At the same time, we may have different kinds of accelerators, And in this case, in addition to the other different accelerators that you might have, for instance, GPUs or hardwire accelerators for machine learning, I will consider a programmable many core accelerator. That is an accelerator that is suitable for both single program, multiple data type of parallelism, as well as for multiple program, multiple data types of parallelism. And this is because in the high-end embedded computing domain, you have that data parallel sections in the code are alternated with irregular task level parallelism. And for that, it has been demonstrated that having also among your set of accelerators a programmable many core accelerator may be a very good option. And so you can think of offloading some critical computation kernels from the IoT service running on the separation kernel on the host system onto the programmable many core accelerator. And the consideration that I'm gonna make for this kind of accelerator can be extended to all kinds of accelerators. And the point is that what is the most effective way of sharing accelerators? Some accelerators that cannot be spatially partitioned. Therefore, the only way to share them is through time division multiplexing. Another way to share parallel accelerators is through spatial division multiplexing. But first, let's look at the programmable many core accelerator architecture first. It's a bidimensional grid of computation clusters, and cluster-based architectures are currently mainstream in the high-end embedded computing domain. You think, for instance, about the CalRay MPPA architectures, the Platform 2012 architecture, and so on. Moreover, here you can see that for each computing cluster, you have a distributed bank of L2 memory. So the memory organization here is distributed shared memory. When we zoom into a computing cluster, we can see a number of processing cores with their own local instruction caches. And then we have a shared L1 data cache, which is, however, software control. Without lack of generality, here we consider this software control, so explicitly managing software. That's why here you have a DMA, and with this DMA, you can bring processing data onto your L1 or onto the L2, and you can process data from there. The focus of the technical material that follows is on effective sharing of the programmable many core accelerator among IoT services that are offloading their computations. So, how to effectively share the many core accelerator? We can use elasticity for that. Elasticity means that each Internet of Things service, which is running on the host processor, should adhere to the principle of using just what it needs at a given point in time. So do not allocate resources for the worst case, but keep asking for what you need, and what you need changes over time, because typically these IoT applications have fluctuating workloads. This pretty much depends on their phase, and it pretty much depends on what's going on in the surrounding environment. So what could be a feasible scenario capitalizing on elastic computing is the following. At some point in time, you share your many core accelerator among IoT services. And so you associate a compute and memory partition to each IoT service. But the partitioning pattern is allowed to change at runtime, because you have a resource manager which monitors application execution, which collects requirements for more or less resources from applications, or that proactively takes resource management decisions in order to optimize the execution state. Therefore, at a given point in time, you may decide that some partitions associated to corresponding services may have to shrink, and some other partitions may have to enlarge because they are becoming more critical. And therefore, you may have a lower level optimization framework that takes care of determining the next shape of partitions depending on the target size. Therefore, this could be the resulting partitioning pattern. And again, in order to do that, you need to implement flexible and fine-grained provisioning of resources to applications. That's the basic concept. That's the basic way to capitalize on elastic computing in order to efficiently share resources at the infrastructure edge. But the point is that now we are in trouble because current hardware software architectures are not ready for such dynamism. And there are a number of reasons for that. So first, you need applications whose level of dynamism can change over time. And it's not straightforward to do that, to dynamically change the level of parallelism on the fly. You could have special runtime support for that. You could use code versioning for that. It's anyway an overhead. And therefore, now the question is, what is a programming model to sustain this vision? Okay, these are still open questions. Moreover, you need a hierarchical resource management framework. You need the top-level resource manager that has visibility of application metrics, of application quality of execution, and you have a lower-level manager that takes care of partitioning, that, for instance, takes care of determining the next partitioning pattern for the new epoch. And here, artificial intelligence may play an enabling role to solve this problem. Moreover, we need to enforce secure grade isolation between partitions throughout the entire platform, not only on this accelerator, but also throughout the entire platform. So you need to enforce spatial or time isolation between running services. And here I will demonstrate in a while that an effective way of delivering isolation is through the control of the network on chip routes. As a result, because of changing partition shapes and sizes, then your network on chip routes have to change at runtime. Now the question is, we are not used to systems that dynamically change the routes of their packets. So what is a suitable reconfiguration mechanism to reprogram the routes of your network? Moreover, every partition needs to access memory controller access ports. And one solution would be to reach them through invasion of other partitions, but this is at odds with security requirements. So how to avoid network on chip interference while still being able to access memory controller access ports that are instantiated at the boundary? Ideally, all partition shapes should be routable to give you maximum flexibility. So you may want to have the flexibility to allocate arbitrary partition shapes. But now the point is that for networks on chip, it's not trivial to support arbitrary partition shapes while keeping the routing logic lightweight and keeping the routing paths efficient, that is, keeping to pursue minimal path routing. So the more the flexibility that you enable, you will see, the higher the constraints that you're placing on the computation route, on the routing computation logic, and on the efficiency of your routing paths. Last but not least, it's not a mystery that several government programs require for millisecond range reconfiguration. And in order to achieve these very aggressive reconfiguration times, you need to have vertical integration of both software and hardware support. Now, the good news here is that all the red bullets have something to do with network on chip, and therefore network on chip support can help to effectively tackle these challenges. Finally, we hit the bottom, so we reached the lower layer of the software stack, that is the on-chip interconnection network, that as a system integration framework has to do with most of these issues. The question is there anything like this already in the market? So the most similar things that I've seen, the most related thing that I've seen is the Tailera tile many core architectures that have been currently incorporated into the Mellanox portfolio of processing architectures. And these Tailera tile architectures are using a very advanced network on chip, which is called the iMesh network on chip technology. Actually, they are instantiated not one, but 5 networks on chip, each one customized and dedicated to a different traffic pattern. Now, the point is that on top of these many core architectures, they have, I think, up to 100 core architectures, you are allowed to define virtualized computing islands. So you can identify computing islands, and you can have your own operating system running inside the partition with its own applications. And the isolation between these partitions is achieved through the Tailera's patented hardwall network on chip link protection scheme. So they have a link protection scheme, and with this hardwall protection scheme, individual links in the network can be blocked from having traffic flows across them. So if some malicious entity tries to inject traffic from one partition to another partition through a forbidden link, this will be immediately detected by the system, especially by the hardware, which will notify this to the operating system, to the host operating system, and this is going to kill the violating process. So this is already a first example of hardware support for partitioning. However, this hardware support is, to my knowledge, very static. So you can statically configure these virtualized computing islands, and there is no explicit or effective support to reconfigure these settings on the fly for fast adaptivity to what's going on in the environment, okay? Moreover, you have link controllers in order to check for link injection violations. And these link controllers that are represented here in this picture, they actually introduce delay over the links. And you know that in networks on chip, links are typically if the switch is properly pipelined, links may turn out to be the critical path. And so we are adding stuff to the critical path, which is not good. Moreover, here they're using XY dimension order routing. So they are routing packets at first along the X direction and then along the Y direction. So X and Y routing. It's a mainstream routing policy for regular networks on chip, which means that they can only support squares and rectangles. They cannot support irregular partition shapes. And in case they had a partition shape and they kept using X and Y routing, what would happen is that this packet that goes from this source to this destination would end up invading the green partition and to be derouted to the south in order to reach the intended destination in the blue partition. So you would end up having partition invasion, which is not good for security, predictability, composability, reliability, and so on. Another critique that we can have with respect to this hardware solution is that they handle violating processes as an afterthought and not from the ground up. That is, they do not prevent illegal routes from the ground up. So clearly, it's possible to integrate control for violating processes deeper into the routing mechanism of the network on chip. Anyway, this is a very instructive example. The key takeaway, in my opinion, is that routing control of the routing path, can be an effective way to enforce isolation, to support isolation from the ground up in hardware. But the field is still largely in the early stage. So we need to familiarize with how routing mechanisms look like in an on-chip interconnection network. And this is a background slide. So how can you control the NoC routes in your network on chip? It depends on what kind of routing mechanism you are using. Don't confuse the routing algorithm, the strategy that you use to route packets to destination, with the routing mechanism, which is the way you implement this routing algorithm in hardware. There are two fundamental ways of implementing a routing algorithm. The first way is called source-based routing. So you have your CPU that has a load and store address, and with load and store address, you fundamentally go to a lookup table, and from this lookup table, you derive directions, routing directions that you should take at each switch in order to reach the intended destination. For instance, the routing directions sound like at the first switch turn south, at the second switch turn east, and so on, till you get to the destination. So all these routing directions are embedded into the packet header. So these are the main features of this routing mechanism. You don't have to perform any routing computation in your switches. No, it's so to say zero delay routing computation in the switches, because the switches just strip of header the routing directions that they have to enforce. So there is no computation for them. But this is not an adaptive strategy. Adaptivity means that in the switch, you take decisions about routing based on in situ actual operating conditions. It's topology independent, because the switches that you're using here, you can use in whatever topology you may think of. But there is a significant scalability limitation, because fundamentally here you have in your packet header, you have the routing directions. And how many routing directions you have here, you need to reserve space for as many routing directions as the worst case number of hops in the packet. Okay, so you need to reserve space in the packet header in order to embed the directions for their furthest away destination. And this means that as you keep scaling up the network size, your packet header will be more and more an overhead. An alternative mechanism is table-based distributed routing. With this mechanism, you fundamentally embed in your packet header only the identifier of the destination. For instance, the coordinates of the destination on a bidimensional grid. Then you use this destination identifier in the switch to enter a lookup table, and the lookup table returns the direction that you should take at this switch only. Okay, so this switch says, okay, you're going to that specific destination. If you want to go there, then at this switch, I let you go out to the west. That's the way it works. So this is more appropriate for adaptive routing, because you can put multiple routing options in these local lookup tables. You have a routing delay penalty at this switch, because in each switch you need to access the routing table, and accessing the routing table takes time, and it's also an area and power overhead. Again, the lookup table is the inherent source of a scalability limitation, because as you keep increasing the size of your network, you need to increase the number of entries in your lookup table, the slower your lookup table becomes. So again, this has scalability limitations. There is a common feature between these two routing mechanisms. They both use routing tables to store routing algorithms. So the information about the directions to be taken based on a specific routing algorithm, they are stored in entries of the routing tables. Okay, so now let's use this traditional network on chip routing technology to support our flexible partitioning in the target fog node, in the forward-looking fog node. So at runtime, we may have to move from this partitioning pattern to these different partitioning patterns, where some applications have gone, some other applications have come, or existing applications have been resized. So how would you handle that? So first of all, we need to use a topology agnostic routing algorithm. For instance, X and Y doesn't work here because X and Y works only on a regular square, on a regular rectangle. But if you want to support arbitrary partition shapes or flexible or some flexibility, you need to revert to a routing algorithm that can route packets in any kind of topology. They are called topology agnostic routing algorithms. But there is some task to do to adapt each routing algorithm to the partition shape at hand. Then you may want to keep the routes within the partition boundaries, and in this way you ensure isolation. And you will compute the routing paths based on the topology agnostic routing algorithm in your partition, and you will program your routing tables accordingly, this way delivering flexibility. So what happens is that at runtime, when you need to reconfigure your partitioning pattern for a new partition size or shape, you need to take the following course of action. Let me tell you this to you again. This is a runtime reconfiguration overhead. For each partition of the new scenario, you need to do the following things. You need to customize the topology agnostic routing algorithm for the new partition shape. For instance, some routing strategies build a minimum spanning tree out of your partition nodes. So you need to build a spanning tree. Then they enforce some routing rules throughout the spanning tree. And the second course of action to be taken is to compute the routing paths. To compute the routing path based on this customized topology agnostic routing algorithm. And this way you derive the information to populate the routing tables that needs to be programmed. And finally, once all routing tables of your new partition have been programmed, you can resume execution. There are a number of evident limitations of using current NoC technology for flexible partitioning. So, first of all, routing tables are typically large, slow, and they do not scale at all. So they are borrowed from off-chip interconnection networks. They are implemented in many on-chip interconnection networks, but they are not the most efficient solution because they take access delay, they take area, and they take power. Moreover, having to customize your routing strategy to the partition shape at hand, it's a large overhead. It is as though you had a different routing algorithm for each partition shape. So a different way of saying that is that you have too many routing algorithms. No, you have a per partition routing algorithm, and it's too much of an overhead at runtime to configure that. So let's now try to solve both of these problems, starting from the latter. You have too many routing algorithms. So the point is, why not using a single global routing algorithm? You use a global routing algorithm for the network as a whole, regardless of the partitioning pattern. Does it work? Well, typically routing algorithms, such as X and Y routing, illustrated here, are global and statically defined. You define the global routing algorithm at the design time. And it holds for the network as a whole. But when you start inferring partitions, then if you follow X and Y with this partitioning pattern, what happens is that you end up invading this red partition, which is not good for security, predictability, composability, reliability, and so on. Moreover, there are some partitions that may end up being unconnected, because if you are using only X and Y, and if you want to go from this node to this node, and you can use nothing else than X and Y, then you are not allowed to enter this partition, assuming that we found a way to enforce partition boundaries. So assuming that we found a way to solve this problem, then there is no way you can connect this node to this node because you would need X and Y. you cannot use multiple routing strategies at the same time, such as X and Y or YX. Because if you start mixing routing algorithms on the same network, then you end up in deadlock problems. Last but not least, there is a common pragmatic solution to all these problems. And this is what people that have done some research in this field typically assume. They assume as legal partition shapes only squares and rectangles, because this makes life simpler. Because if you use squares and rectangles, they are perfectly compatible with the X and Y routing. Okay, therefore, by construction, all the routing paths will be contained within their respective partition shapes. Okay, there is no situation like this that may happen. Squares and rectangles certainly deliver isolation by construction if you are using a minimal path routing algorithm, but they unacceptably limit flexibility, in my opinion. So we need for something better. Okay, now we will go back to the problem of supporting a global routing algorithm later, because first we have to solve the problem of routing tables. Can we envision tableless routing? There are several proposals around. I will propose one of them that has its own distinctive features. And the first one is to have logic-based distributed routing. So let's say at every switch, you have a routing computation stage, which consists of simple computational logic. It has to be simple, but at the same time, it doesn't have to be hardwired. Otherwise, you miss the flexibility property. You miss the dynamic reconfiguration property. So it has to be routing logic, but it has to be flexible. At the same time, this means in practice that we will need some form of configuration bits, configuration registers for this kind of routing logic. But these configuration registers should be as small as possible in terms of the bit width, because we need to keep the reconfiguration overhead at runtime low. So let's see here a key idea that was worked out at first by Polytechnic University of Valencia, and then later this was a topic of a collaboration with myself for the efficient implementation in a on-chip environment. So the idea is to express a routing algorithm in terms of what this routing algorithm prevents you from doing. So express a routing algorithm in terms of the forbidden turns that it introduces for deadlock-free routing. Think about X and Y routing. In X and Y routing, you can route first in the X direction and then in the Y direction, so you cannot do YX, because if you do also YX, then you may have deadlock, no? Which is a blocking condition for the traffic. So as you can see here, we have arrows. These arrows indicate what you cannot do with X and Y routing. You cannot do YX, and that's why you have an arrow here. So all these arrows indicate what is forbidden, what you can't do with this routing algorithm. Okay, so a legal routing path will have to fulfill the requirement posed by these routing restrictions. And the same formalism you can apply to other routing algorithms, such as horizontal segment-based routing, vertical segment-based routing, up and down routing, and so on. And with the difference is that these routing algorithms are topology agnostic routing algorithms, while X and Y works only for squares and rectangles. But for every routing algorithm, you can express what a packet is not allowed to do, the forbidden terms for the sake of deadlock-free routing. Then the second idea is to combine this formalism with a routing logic that in a distributed way finds the packet's way to destination while fulfilling the obligations posed by these routing restrictions. So you need a distributed routing logic that is able to interpret at least the nearest routing restrictions and to route the packets accordingly. Whatever direction that you can select that approaches the destination and that meets the routing restrictions, then this is a legal routing path with that routing algorithm. And this actually enables also some form of path diversity. There may be several legal ways to reach a destination. Let's see how this routing logic works. And the routing logic that interprets these routing restrictions as a name, it's called logic-based distributed routing. So again, routing restrictions are a specific way to look at routing algorithms, and maybe other ways. And they turn out to work pretty well. So consider a packet now that is entering this switch here. And the packet in its header carries the destination coordinates. And the switch has its own local coordinates. The first thing that the routing logic does is to compute target quadrant. So assume we are here, and we want to go here to the destination. So first of all, we compute the target quadrant. And in this case, the target quadrant is the northeast quadrant. Then we determine productive directions to reach a destination in the northeast quadrant. What are the productive directions? They are clearly north and east. Now we evaluate the alternatives. So the point is that we take north only, and here we need to introduce a conservative routing criteria. We go north only if the next stop it's possible to turn east. So only if the next stop it's possible to approach a destination. So this routing mechanism is highly targeted for shortest path routing. So I take north only if you guarantee me that the next hop I will be able to approach a destination. You never know. Maybe I want to keep going north, but at least you need to provide me an escape path to go east because my destination is to the east. And in this case, there is an arrow here, there is a routing restriction. And this switch should be aware of the routing restrictions on in the neighboring switches, and therefore this switch will never route the packets to the north because at the next stop it's not possible to approach the destination. A better option is instead to take the east direction, because if you go east, the next stop it's completely possible to turn north to approach the destination, which is to the north. Therefore, the packet is actually routed to the east port. And so on. You can iterate the same routing computation, simple routing computation at each hop. There is a very nice feature here that LBDR, logic-based distributed routing, works in quadrants. And this is a support for scalability from the ground up, because the quadrant can be arbitrarily large. We simply don't care. We only want to know whether a destination is in the northeast quadrant or not. And the northeast quadrant can consist of 4 cores, 16 cores, 1 million cores. We actually don't care. It's not like routing tables that need to have one entry for each possible destination. So it's very scalable as an approach. Moreover, it's logic-based. Yes, it's routing computation, but it's not wild, because this can be programmed. How can you program that? You can program that by reprogramming the routing restrictions. You want to change the routing algorithm, you change the routing restrictions, and each switch will be made aware of what the routing restrictions in the neighboring switches are. Okay, so this is actually reprogrammable through the reprogramming of the routing restrictions. And this strategy has been demonstrated to work perfectly for it has been tried out with the most relevant topology agnostic routing algorithms. It's providing similar or even better performance with respect to table-based routing, with the difference that it finds the routing paths on the fly. And the point is that, we see the implications of this, is that it supports all the topologies that allow minimal path routing. And this is kind of a trade-off with flexibility, and I will talk to you about this in the next coming slides. First of all, let's try to realize ourselves that this is bringing you benefits with respect to table-based routing. So here in a 130 nanometer technology, we use the memory compiler to generate routing tables, and we measure the area of the routing tables and the access time of to the routing tables. And we did that for a growing network size, from hundreds to thousands of cores. And you can see that here the horizontal line is the LVDR overhead. As you can see here, the overhead of LVDR in terms of area and access delay does not depend on network size because it works in quadrants. And therefore, this is a very scalable solution with respect to the routing tables that instead have a huge overhead as you increase the network size. So we have found out a way of performing tableless routing, which is very lightweight, which is, so to say, in terms of the overhead it introduces, is in the same order of magnitude of source-based routing while not using routing tables. Let's go into some implementation details. Every switch, for instance here switch number 5, needs to have some configuration bits of the routing logic. And the most obvious configuration bits are the routing restrictions for the next hops. For instance, here you have routing restriction routing northeast, which means that if you route a packet to the north, okay, and then you want to go east, this is legal. There is no restriction to do that. So the routing restriction is equal to 1. Instead, if you want to go to the south and then to the east, you cannot because you have this arrow here. So routing southeast is equal to 0. It means that it's not a good idea to go south if your destination is further to the east. However, the idea is to extend this mechanism to support partitions. And that's very straightforward. How can you define a partition shape? We simply need to introduce additional configuration bits, in particular one configuration bit for every direction, which tells you whether the switch is connected along that direction. So for instance, to the north, this switch number 5 is connected, connectivity to the north equal to 1, and to the east, this switch is not connected because there is a partition boundary, so you set the connectivity bit to the east equal to 0. So setting connectivity bits, which are additional configuration bits, but only 4 per switch, setting connectivity bits to 0 means that you are denoting rigid fences for your partitions. You're defining rigid boundaries that cannot be crossed by traffic. So your routing logic will never route a packet to a direction where the connectivity bit is equal to 0. So you have routing control for violating processes and deeply embedded into the routing logic. And the overhead is pretty lightweight. If you think about it, it's overall 12 configuration bits, per switch. And therefore, if you want to reconfigure your routing algorithm, if you want to reconfigure your partition shapes at runtime, you just have to reprogram 12 configuration bits for each switch and not entire routing tables. So this fulfills the goal of coming with a low reconfiguration overhead. However, it's not a perfect solution because we have flexibility limitations. It's not a routing table. So to say, it's a very small routing table. It's a 12-bit routing table. So it supports reconfiguration very efficiently, but it poses a trade-off on the level of flexibility that you can achieve. And let's try to understand this. So the source of the flexibility limitation is minimal path routing, because this approach is targeted to minimal path routing. Okay, it always strives to find the shortest routes to destination. So if you are in a situation like this, if you have a partition shape like this one, which is quite irregular, it has a U shape here, you can see here, and it means that you have another nested partition, no? With this one, and you have a packet that from A wants to reach B, this routing logic will say, what is the target quadrant? Oh, it's northeast. Then productive directions are north and east. But to the north, the connectivity bit is 0, and to the east, the connectivity bit is 0. Therefore, the routing logic simply bails out. It doesn't know how to reach a destination. Okay, it's because the routing logic has only 12 configuration bits, right? if you have a higher number of configuration bits, that is a routing table, then it's possible to find the routing path to every possible destination in arbitrary partition shapes. But there are solutions to work around this limitation. In this case, one solution is that when the routing logic bails out, then you introduce additional programming bits that indicate a deroute option to the programming logic. And in this case, you may introduce the routing option to the south. So when the routing logic bails out, it will take the derouting options, and therefore it will take the derouting option allows you to reach this switch. And from this switch on, the baseline LBDR mechanism is enough to find the path to the destination. So the way out is the route option. However, the question is, how can we compute the route options at runtime? And that's a tricky question, because it's not straightforward, because typically you have to try out all the possible combination, or at least there is not enough research on how to do that at runtime. Or you could store these routing restrictions from offline analysis, but then you end up in a large memory footprint. So for the time being, this is an open research question, how to provide the route bits in an efficient way. Another flexibility limitation arises in partition shapes like this. They are even more irregular. In this case, you have a packet in B that may be routed to either destination C or destination A. But here there is something strange for LBDR. And the something strange is that you cannot say, okay, all my destinations are in the northwest quadrant, therefore I take west. Because if you take west, it's true that you will be able to achieve A, but if you take west, you cannot reach C, because here you find a connectivity bit to 0. So there is no unique direction for every quadrant. But actually, in this case, the productive direction is strictly destination specific, which means you would need a routing table. So it's not possible with LBDR to safely route this partition shape. But again, there are solutions to work around these limitations. For instance, you may think of duplicating the packet here. In packet B, you create 2 replicas of the same packet. You do a fork. And then, for instance, if the destination is A, one replica will reach the destination, and the other replica will simply stop here. And when the LBDR logic bails out, you will simply discard the replica. But when you introduce forks, then your network on chip is not deadlock-free anymore, and you need to change the switching strategy. You need to change it from Walmart switching to virtual cathode switching, which means that you need to implement a lot more buffering, and therefore this solution might not be that cost-effective. Okay, so you have some flexibility limitations, but if you think about it, it's you still have a lot of flexibility, okay? And the flexibility that you are allowed is to instantiate partition shapes that still enable minimal path routing. You know, here the downside is that from A to B, it's not minimal path routing for the baseline to the mesh. And in this case, you are actually explicitly violating the LBDR principle of one destination, of one direction per quadrant. Okay, but if you recognize this situation, you can forbid this kind of fancy partition shapes during routing, during resource management. Okay, you can forbid to allocate this kind of fancy partition shape, and the mechanism still works. Still, you have a lot of flexibility, as you will see later. Okay, now let us decide to stick to legal partition shapes, to the partition shapes that can be routed with an LBDR routing mechanism. And now let's wonder whether you can use LBDR in conjunction with the global routing algorithm in such a way that you don't have all that runtime overhead to recompute the routing function on the different partition shapes. And we can see here that there is a problem. This is not a problem of LBDR. It's again a problem associated with the global routing algorithm and with inferring partitions on top of a global routing algorithm. So as you can see here, you have two partitions and you have a specific routing algorithm that is encoded by these routing restrictions. And you can see that if you have a packet from 12 that wants to go to 2 in the right-hand side partition, then there is no way to turn north because you have routing restrictions here. Why you have those routing restrictions? Because these routing restrictions have been placed to forbid, to prevent deadlock on the topology as a whole. Okay, we don't want to customize the routing algorithm for this partition shape, and that's why we are in trouble now. Because now this partition shape is not compatible with the underlying routing restrictions, with the underlying global routing algorithm. And in fact, if you change the underlying routing algorithm, then in this way, for instance, you change the arrows while still preventing the formation of cycles, then what happens is that now these two partition shapes are perfectly compatible, are perfectly matching the global routing algorithm. So in order to solve the problem of legal partition shape, because this partition shape here, it's legal for LBDR. LBDR works in this context. But the point is that routing restrictions are placed with respect to the network as a whole and not with respect to the partition shape, to the point that the shape and the routing algorithm are not compatible. How to solve this problem at runtime? We have two possible solutions. The one is represented here: adapt the global routing algorithm to the partition shapes on the fly. You need to pay attention because when you change the routing algorithm, previously existing shapes could become infeasible. So you need to select a proper routing algorithm, and you need to handle the reconfiguration transit. And there is a way to do that. It's called OSR. I don't have time to present it. And I will now skip the first approach and go to what I think it's the most interesting approach: selective masking of routing restrictions at runtime, which we call the PLBDR, so the partition-enabled LBDR. So what's the PLBDR philosophy? So first of all, for the time being, PLBDR accepts the flexibility limitation of the baseline LBDR. So the legal partition shapes are those that still enable minimal path routing on the 2D mesh. And we will see a number of examples of legal partition shapes. And the flexibility is well beyond the limitations of squares and rectangles. Okay, we have new degrees of freedom, even though not arbitrary degrees of freedom. But I think it makes sense to find a trade-off. Moreover, the key intuition is the following. So this is the example of a deadlock condition. The blue packet wants to turn east, but it can't, because this path is already allocated by this packet. That wants to turn north, but it can't, because this path is already allocated by the red packet, and so on. There is a cyclic dependency, and in the end, the traffic is blocked. In order to prevent the formation of these cyclic dependencies, deadlock-free routing algorithms introduce explicitly or implicitly routing restrictions. And this routing restriction is such that this packet here, the bottom, will never try to turn north because this is simply forbidden by the routing algorithm. And therefore, you will never have a cyclic dependency here. But once we establish partition boundaries, then the partition boundary itself is a way to solve the deadlock problem, because it is as though we were preventing this cycle. Okay? Since you cannot cross this boundary, and you cannot cross this boundary, it's even more conservative. So you will never have a cyclic dependency here. And so it's useless to have this routing restriction. At the same time, this routing restriction should be considered for different partition shapes. For instance, for a partition shape where all the 4 switches belong to the same partition, then it makes sense to consider this routing restriction. So now the basic idea is, can a distributed routing logic detect that we are in this kind of situation and selectively mask this routing restriction? Well, actually, this is possible. Let's look at this example. We have a source here, we have a destination here, and the packet goes to switch number 13, and if you don't do anything, it will be forbidden to turn north because of these two routing restrictions that have to do with the global static routing algorithm of the network. So what we can do here is to say at switch number 13, what about my connectivity bit to the north? Wow, connectivity bit to the north is 0. It means that I am traveling along a partition boundary. Therefore, at the next hop, if I find a routing restriction to the north, it doesn't make sense. Why? Because it is closing a cycle with switches that belong to a different partition. So this deadlock will never occur. Therefore, the approach is simply to discard this routing restriction. You see? So the packet is routed as though the routing restriction at the next hop were not existing. So I am selectively masking routing restrictions by monitoring the connectivity bits, by monitoring whether the packet is traveling along partition boundaries. Now, this new partition shape is fully connected. So PLBDR works with the global static routing algorithm. Therefore, it doesn't have to deal with the runtime reconfiguration of the routing algorithm. It's already there, and we lay out, so to say, partition boundaries on top of a pre-existing static global routing algorithm, and we selectively mask routing restrictions where needed. Another question that we have to, problem that we have to solve. Okay, now we are dealing with this network where I am implementing spatial division multiplexing, but if I have this partition here that wants to reach this memory controller, how may this happen? How can this happen? Because I will need to invade other partitions. It seems that an effective solution following the iMesh approach of the Tylera type processor is to instantiate multiple networks on chip and possibly lightweight ones. And in this case, there is a perfect synergy if we instantiate a network on chip which comes with spatial division multiplexing, the top layer, and we implement another network on chip that implements time division multiplexing in such a way that you can reach the memory controller by using an isolated time slot. So you preserve isolation at first in space and when needed in time. And there is today an intensive research to come up with a time division multiplexing NoC that implements as few buffering resources as possible, because the Achilles heel of time division multiplexing for NoCs is the instantiation of a large amounts of buffers. But there is promising ongoing research to build time division multiplexed NoCs inspired by the channel dependency graph, and that can minimize the amount of instantiated resources. So yes, true, you have a dual network on chip, but the second one is as lightweight as possible. And the vision here is that these partition shapes should be elastic, so they should be dynamically reprogrammable in shape and size. And also, the time slots that you have in the TDM network should be reconfigurable in duration. So the amount of slots that you have there depends on the amount of partitions that you have at a certain amount of time, and the duration of the time slot should be customized for each partition. And again, a fully flexible time division multiplexed NoC is an active research issue. You could also think of exploiting synergies between the two networks. For instance, when LBDR bails out in the top layer, you may use the TDM NoC as an escape path. But okay, these are wild and crazy ideas that are coming. Some experimental results, because it's time to converge. So let us consider an 8x8 multi-core programmable accelerator, okay, the one which is represented here with the dual network on chip scheme. And let's try to simulate the reconfiguration of this accelerator In this case, we generate in a random way 17 consecutive partitioning patterns, where we evolve for one partitioning pattern to the other by taking random decisions about reshaping existing partitions and about partitions that come and go. And so we end up having 17 consecutive partitioning patterns, and we want to assess the overhead for reconfiguring the network on chip when going from one partitioning pattern to the next one. We compare table-based traditional routing mechanism that for every partition in the new scenario, it needs to customize a topology agnostic routing algorithm and to find the routing paths to program the routing tables. We are using here segment-based routing, which is a topology agnostic, in this case, a shape agnostic routing algorithm. And the way it works is that for every new partition shape, it splits the partition into segments based on some criteria. And in each segment, it introduces routing restrictions in such a way that all the legal routing paths will be deadlock-free. Then you solve an optimization problem. You find the shortest path in this new scenario, and then you populate the routing tables. That's a standard, that's a way a standard state-of-the-art table-based routing approach would work, coupled with shape agnostic routing. There are other approaches that do not use tables, but they are not strictly aiming at shortest path routing. Even in case shortest path routing is possible, they end up taking non-minimal paths, suboptimal paths. So it's actually a trade-off. LBDR doesn't take this approach. It prefers to limit flexibility a little bit, but to always try to take the shortest path route to the destination. And in fact, we are comparing this with PLBDR. And the only runtime overhead of PLBDR is to just reprogram the connectivity bits, not even the routing bits, because the routing algorithm is global and stays the same. So we just have to reconfigure 4 boundary bits, 4 connectivity bits for each switch at runtime. So here we can see on the x-axis the partitioning pattern from 1 to 17, on the y-axis the hardware reconfiguration cost. How do we measure the hardware reconfiguration cost? In terms of the amount of information that we need to reprogram. So in a network on chip, the smallest amount of information that can be sent around to reprogram things is called the fleet. And in this case, it's actually a 32-bit word. So how many 32-bit chunks of information we need to reprogram in the system? We can see that in table-based routing, the cost is that we need to reprogram the lookup table entries. And we express the amount of lookup table entries to reprogram in terms of these 32-bit chunks. Consider that we are trying to minimize the reconfiguration overhead. In fact, we only reprogram the entries that lead to other cores in the same partition. So not all the entries of the network, doesn't make sense, but only the entries that lead to other cores in the partition. And if by chance the entry doesn't change with respect to the old partitioning pattern, we don't touch the entry. Nonetheless, you can see that the overhead to reconfigure from one partitioning pattern to the next one, it's from 500 fleets in the best case to more than 4,000 fleets in the worst case. And here there is a breakdown. There is the amount of information that you have to reprogram for every partition. Okay, so we can look at the grand total. So the order of magnitude is hundreds of thousands of fleets to be programmed during a reconfiguration. For PLBDR, remember that we need just to reprogram 4 bits for every switch. And in order to do that, we conservatively assume a 2-fleet reconfiguration packet for every switch. So overall, it means that the overhead for LBDR is only 128 fleets. Okay, 128 fleets, which is typically 1 order of magnitude lower than table-based routing, okay? And this is hardware reconfiguration cost, no? The reconfiguration overhead to reprogram that you pay in hardware. So these are actions that the network on chip can automatically take in order to reprogram the routing paths and the connection boundaries. But we also have a software reconfiguration overhead. I'm not talking about the overhead to change the application level parallelism. This is another stuff. What I'm talking about is that the software needs to do something to reprogram the NoC. And in particular, we know that in table-based routing, there needs to be some software entity that either computes the segments for the new partition shapes, or instantiates or derives a minimum spanning tree out of the new partition shape, and that finds the routing path. And in case there are multiple routing paths between any source destination pair, it tries to select the routing path in such a way that the total link congestion is minimized, okay? And so you can see that there are some things that have to be performed in software and that enable the hardware configuration of the network. And by running on this 2-core Intel machine at 2.7 gigahertz and 2.9 gigahertz respectively, this is the software overhead for the table-based routing. It amounts to milliseconds, okay? Most of the time is spent to find smart routing paths on a partition shape where you have assigned routing restrictions. So to find the routing paths based on the customized version of the topology agnostic routing algorithm on that partition shape, it takes several milliseconds, and this adds up to the overhead of building segments and assigning routing restrictions, which is the blue overhead here. So the BLBDR has no software overhead at runtime. There is nothing to be recomputed. We don't have to recompute the routing function because the routing function is global and static. But just for the sake of comparison, we are reporting here the design time overhead of PLBDR, because PLBDR at design time needs to find the routing restrictions for the network as a whole. It needs to compute the global static routing algorithm. And it takes much less than what it takes to table-based routing at runtime. The reason is twofold. First, this procedure is invoked once for the network as a whole, not for the different partitions that you have at some point in time. Moreover, it just needs to compute the routing restrictions, and to program the routing restrictions in hardware, it doesn't have to find the routing path, because the routing paths are automatically found by the routing logic at runtime. And that's why we have only slightly more than 1 millisecond, which is paid once at design time, and nothing is paid at runtime from the software viewpoint. Okay, I think that we have reached the conclusion. Today, a new trend is to co-design network on chip with the system architectures, but I try to convince you that this can be further extended to co-design your network on chip with a system of systems. And in particular, we saw that a new IoT ecosystem can be developed only around a cloud things continuum, which is not there yet. There is today simply a simple compute hierarchy, but not a true functional cloud things continuum. And a way to put all the things together in future cloud things continuum solutions is to revolve around elastic computing. And this poses new requirements, new design requirements on shared for computing nodes that are shared among different IoT services, where you have to implement strong isolation and flexible repartitioning of compute and memory partitions. And we saw that an effective support to make this happen and to fulfill these requirements is to control the routing mechanism of the NoC, because we can provide the basic hardware support for isolation and for dynamically reprogramming the isolation boundaries. The basic idea is to avoid table-based routing, which is mainstream in off-chip interconnection networks and also in many on-chip interconnection networks, and to use distributed routing logic, which pays a trade-off, yes, between fast routing computation and flexibility. It has some flexibility limitations. Still, all the partition shapes that imply minimal path routing on the baseline 2D mesh are legal. So you can have L partition shapes, you can have P partition shapes, cross partition shapes, T partition shapes, and so on. In order to avoid the runtime recomputation of a routing function for each partition shape, for each new partition shape, then we may want to use a static global routing algorithm, and we may want to implement some intelligence in the routing logic to selectively mask routing restrictions that are useless for the sake of deadlock avoidance, but that still prevent the routing of some legal partition shape. Overall, this LBDR approach is a trade-off between shape flexibility and performance hour and power overhead of your routing computation stage, and it enables overly fast runtime reconfiguration. Only 4 bits to be reprogrammed for every switch. In future work, we will try more cost-effective solutions of working around the limitations of the partition shapes. We know that there are current solutions to work around such limitations, but they still have some weak points, and we will try to improve those solutions to provide even higher levels of flexibility. And we are currently building the management framework on top of this dynamic hardware, so to say. And I am establishing lots of interdisciplinary collaborations with academia and industry to build the layers on top of this. That is a suitable programming model for this landscape, a suitable orchestration mechanism for this, and overall to build a continuum around this basic network on chip support for isolation and for flexible repartitioning. Okay, thank you very much for following me. And I think that now we can have a 5-minute break if you're interested, and you can post your questions. So we can resume discussions after 5 minutes if you're interested, if you have questions. And after 5 minutes, we will discuss the main questions. For those of you that are not interested in that, I just thank you for following, and let's talk together again next Wednesday. But I will reconnect in 5 minutes to answer questions. Thank you. Let me start immediately because we are approaching the end of this session. There are three very smart and interesting questions. It would be very nice to be face to face because these are questions that don't have a unique answer. They could be the object of a debate of fruitful interaction. So let me show you this. So in the logic-based distributed routing example, can a switch route a packet in a direction that doesn't get the packet closer to the target in case of U-shaped partition? Actually, this is not, that's a smart idea, but this is not compatible with the philosophy of BDR, okay? So you can build on this idea to build a different framework, okay? And I will point you to an existing paper on that. It's called, I guess, I don't know if it's up and down routing or left-right routing. So the point of LBDR is that it always tries to achieve minimal path routing, okay? That's its advantage, and that's its flexibility limit. This leads it to a flexibility limitation. Therefore, in case of U-shaped partition, then it will tend to the destination, although there is a hole in the middle. And that's why we need to, for instance, introduce more configuration bits that allow the routing logic to take different decisions in case this is needed, such as the concept of the root bits, no? But at the root is not, the root concept is not embedded into the routing mechanism from the ground up. It's an afterthought, okay? You are not able to perform routing in an ideal way than use of the root, okay? Because this is the inspiring philosophy of this approach. Another philosophy, which is implemented by this left and right worker, is to account for the possibility of a non-minimal path from the ground up. And in that case, the root is not an afterthought. It's something which is considered from the ground up. But so these approaches have lower flexibility limitations, but they end up taking suboptimal routes even in case optimal routes exist. Okay, so it's actually a trade-off. Then there is this question about using flooding scheme to reconfigure routing for irregular partitions. So maybe here I don't understand clearly the question. We can interact via email, because the way you see it, the problem is not reconfiguring the routing, because for reconfiguring the routing, here we have a separate time division multiplexer NoC, which is an elegant way not to interfere with the main partition at NoC while still being able to reconfigure its switches. So we have the reconfiguration mechanism, so to say, but what is challenging in irregular partitions is to find a route to destination using simple routing logic that has only local visibility. That's the main challenge. A different story is whether you want to use flooding to reach all the possible destinations in an irregular partition. That's correct. This is a proposal that dates back to the early days of a chip interconnection network, but clearly you have a high impact over ongoing communication flows. So it's not the good solution, in my opinion, for predictability. Another very interesting question that would require tighter interaction about the specific use case this question is referring to. I mean, the general question is, in the implementation of a NoC, can nodes operate at different frequencies like DVFS? If so, is it possible that this different frequency domain could cause bottleneck on packet routing? The answer is absolutely yes, absolutely yes. And that's why I was telling you in the beginning that you need to co-design your system architecture with the synchronization scheme of your network, because if you are splitting the network on chip into the voltage and frequency domains of the processing cores, then your routing paths become extremely heterogeneous, and you have unpredictable congestion effects along the links depending on the relative speeds. Okay, so a different approach that I personally prefer more, that I explored in the past, some papers on that if you're interested, was to implement the network on a chip as an independent voltage and frequency island. In this case, you have decoupling of the operating condition only at the boundary. You can put 2 clock FIFOs at the boundary of the on-chip interconnection network. And since having such a widely distributed domain is challenging in terms of the clock distribution, then you can think of mesochronous synchronization. So you can relax the constraints for distributing your clocks throughout the switches of the network. But if you are interested on discussing the implications of this with respect to a cache coherence protocol, we can handle this offline. And even more interesting would be to co-design with an asynchronous interconnection networks, for which I have an important solution that we will present in the next lecture. Last but not least, this is a very, very interesting question. So Kim Petersen says, my impression is that NoCs are becoming more FPGA-like with PLBDR, correct? Yes, you're absolutely correct, because when you start introducing a dynamically reconfigurable platform, I typically talk about dynamic hardware, okay? And to build dynamic software on top of dynamic hardware, then the first thing that comes to our mind is FPGA. So what about, this question says, using FPGAs, directly using FPGAs without thinking about this kind of fancy reconfiguration mechanisms? Well, there are pros and cons. I still feel that these dynamically reconfigurable architectures that are not built on FPGAs still have their own existence right. I'll finish with a relevant example. So first of all, if you go to FPGA, then you lose the clock speed. And here we are talking about networks on chip that are working in the gigahertz range. And we are designing all techniques to sustain the gigahertz range operating speed. Moreover, it's true that in an FPGA you have partial reconfiguration, but in general, it's more tricky to reconfigure things while letting the things going. So in an FPGA, the most straightforward approach is to have static reconfiguration. You stop everything, you reconfigure, and then resume everything. I didn't have time here to present some solutions where actually you can reconfigure your network on chip while you are reconfiguring your software level parallelism. There are ways to do that. There are ways to enable these two reconfigurations flow at the same time, run at the same time, without any hard stop and synchronization point, which is more natural for an FPGA environment. Clearly, if you have partial reconfiguration, this can relieve your problem. Although when you think about partitions that can not only enlarge but can shrink, then I think that also with partial reconfiguration, there's no way of avoiding the blocking of the system while you are reconfiguring it. Last but not least, I think that this dynamically reconfigurable architecture that I presented holds promise of higher reactivity with respect to an FPGA environment. And that's the reason why many times you want to build even these dynamically configurable systems on top of an FPGA. So you may think of using LBDR and the associated network on chip on top of an FPGA fabric. This is typically called as a virtual infrastructure, virtual fabric, a virtual computation and communication fabric built on top of an FPGA fabric. I think that you could use the FPGA for more invasive reconfigurations, while for this kind of fine-grained configurations that shown a dedicated solution is the best way to go. Anyway, it would be nice to keep this interesting discussion via email. So thank you very much for posing this very smart and interesting question. Thanks for following me, and talk to you again next Wednesday. Bye-bye.